welcome to our September general meeting, which is being hosted by the CERN Earth and Space Center of Wayne Foster. Thank you, CERN, so much for helping us out. Our speaker tonight is Kevin Cole, Assistant Professor of Astronomy and Geology at Harper College. Kevin's going to discuss two upcoming asteroid missions, the PSYCHE and Lucy missions. And he's going to tell us all about, these are scheduled, I believe, for 2021 and 2022. Kevin is going to discuss the missions for us and tell us what we hope to learn from the results. So, Kevin, if you're set, could you just take it away?
Okay, so I'm going to stop my video, so that's not in the way. Okay, everybody see that all right?
Yes.
Okay.
Yep.
So what we're going to do is we are going to take a look at two new missions, Lucy and PSYCHE. And basically, I'm going to go through and give you a rundown of why we're doing these missions and why they're so important. And I'm also going to give you a little bit of a update on OSIRIS-REx mission at Asteroid Bennu. They're getting close to taking their sample. So I'll give you an idea what's going on there. So I'm going to start out with a little video to give you an idea what the Lucy mission is all about.
We're excited to announce two missions of discovery. These missions will help us learn about the infancy of our solar system, a period just 10 million years after the birth of our sun. The first mission is called Lucy. Lucy will visit 6 diverse bodies known as Trojans. These Trojans orbit the sun in swarms in front of and behind Jupiter, trapped by Jupiter's gravity. We know very little about these objects. They may be captured asteroids, comets, or even Kuiper Belt objects. The second mission is called PSYCHE. PSYCHE will take us to a very large and rare asteroid made of metal. 16 PSYCHE is the asteroid. It is made of metallic iron and nickel, much like the Earth's core. Scientists believe that PSYCHE may be the exposed core of a planet that was once the size of Mars, but it lost its outer rocky layers due to a series of violent collisions. Lucy launches in 2021 and PSYCHE in 2023. Come along for the ride and follow these and other planetary missions on nasa.gov.
That gives you a little bit of an overview of the PSYCHE mission. So we're going to take a look at PSYCHE first. This is actually a pretty exciting mission because we've had missions to asteroids before and to comets, but we've never had a mission to an iron asteroid. And iron asteroids are thought to be the centers of protoplanets, so the cores of protoplanets. So we really have no idea what they look like. So this will be our first chance to really get a close look at these objects. And with our developing technology, our better propulsion systems, this is enabling us to do some things that we couldn't do with just conventional rockets. So what we see here is our radar images from the Arecibo Observatory. And this is of the target asteroid PSYCHE, and you can see it's kind of hard to tell what it looks like, but it is a good-sized asteroid, and this was taken between November 28th and December 9th, 2015. And the nice thing about these radar images is that, of course, you could take these images no matter what the weather is or whether it's night or day. Then you can string these images together and you get an idea what the rotation characteristic of this asteroid is all about. So these are actually the best views we have so far of this world. Now, this isn't such a little world when it comes to asteroids. These are the 4 largest asteroids in the solar system. We've just spent some time visiting Ceres. Our spacecraft is still in orbit around there doing some extended mission studies. We spent a good year at Vesta, getting a good look at what that asteroid is all about. Pallas and Hygiea are the next two size asteroids. We haven't visited them yet. But where Psyche fits in this, it's about ranked number 10 or 11 in the population of asteroids. So while it's small among these other asteroids like Vesta and Sirius, this is a pretty good sized asteroid we're taking a look at. Some 150 miles to 240 kilometers along its axis. And it's an irregularly shaped body. It's not nice and spherical like Sirius. So this is telling us that the gravity of Psyche is not strong enough to force the shape into a spherical shape. The strength of the material is much stronger than its gravity. So this little mystery asteroid is going to be an exciting one to take a look at. These are the asteroids we have been visiting so far. We've gotten pretty good at this. We have visited all sorts of asteroids, carbon-rich asteroids, rocky asteroids. We visited a number of comets, such as Comet Halley and Borrelli and Temple and Vil 2, etc. And some of the biggest ones, other than Vesta and Ceres, are asteroid Letitia. This is viewed by the Rosetta mission on its way to Comet Churyumov-Gerasimenko. And the Matilda asteroid, which was viewed by the Near-Earth Asteroid Rendezvous on its way to its target asteroid Eros. There's Eros right there. So we're getting better at visiting these, and we're not only getting better at rendezvousing with them, now we're getting more ambitious. We're starting to orbit around them, and we can take long-term measurements rather than just quick flybys. And to give you a comparison, Ryugu and Bennu, these are the two missions right now that are in the process of getting samples returned. Ryugu is the mission flown by the Japanese Space Agency. They've already collected their samples and are on their way back. And Bennu is currently being visited by OSIRIS-REx, and this is Itokawa that was visited by the Hayabusa 1 mission a few years ago and bringing some of the first samples back of an asteroidal body. So we have visited asteroids that are extremely tiny, and we've visited asteroids that are very, very large. So if you take a look at Psyche right here, a lot of times, you know, when you say it's 173 miles in size, it's kind of hard to really imagine that until you compare it to things here on Earth. So here we see the asteroid compared to the state of Massachusetts, and about twice the size of the state of Massachusetts. So this is a really, really big asteroid as far as asteroids go. And something like this, if it would hit our planet, if it was this big, that would be a really big problem here. Fortunately, that's not going to happen. But this particular asteroid was named after the goddess of soul in ancient Greek mythology, and that was actually discovered in 1852 by Annabelle de Gasparis. I don't know if I'm spelling that right. But anyway, that's where Psyche stands. So it stands at about maybe the 10th or 11th asteroid that was actually discovered by astronomers. So what's nice about this mission is that it's going to be using solar electric propulsion. And it's a decent sized spacecraft, about 81 feet long, after these solar panels are extended, about the size of a tennis court. And the spacecraft itself is about 10 feet long and about 8 feet wide. So it's a good sized spacecraft. We've got a lot of nice instrumentation on here that's going to give us an idea of what the physical characteristics of this asteroid is. Take a look at its chemistry, its internal structure, how it interacts with the solar environment and such. So the launch of this mission is going to be in 2022, and using the solar electric propulsion system will take us about 3.5 years to get there. Solar electric is a much more efficient method of propulsion than chemical rockets, and the nice thing about it is with chemical rockets, after the spacecraft is launched by the upper stage, it's all coasting with minor course correction maneuvers along the way. So it may take a bit longer to get there. With a solar electric mission, once it gets launched by the upper stage, it takes a little while for the electric propulsion to really kick in to get a good enough speed going. But once it does, it's steady. We can keep that propulsion on for weeks on end. And then when we get to our target object, we can actually go into an initial orbit. We can change our orbit any way we want to because we got the fuel efficiency to do so. So we are planning on arriving at Psyche in 2016, and the observation period initially is going to be 21 months, doing a complete mapping and study of the property. So by the time we're done, we should have a complete global map of what this asteroid looks like. So launch is planning in 2022 from Kennedy Space Center. In 2023, we're going to do a Mars flyby for a kick. In 2026, we arrive at the asteroid's orbit, and we'll be observing between 2026 and 2027. And if things go as well as all our spacecraft seem to be doing, there should be enough fuel and hopefully enough budgeting to do an extended mission, which is a typical process with these NASA missions. So we might be able to get even a longer period of observation with this asteroid, or maybe even go to another one of opportunity. So here's our trajectory. We're going to launch in August 2022. Now, we really don't have enough energy to make it all the way to Psyche. So we got to swing by a planet and borrow some of that planet's orbital energy. So we're going to swing by Mars in about May of 2023, and we're going to steal a little bit of Mars's orbital energy and add it to the spacecraft, and that's going to enable us to do this nice arcing trajectory here and rendezvous with Psyche in January 2026. What this means for Mars is that we're gaining a few meters per second in our velocity as we head out to Psyche, and Mars is losing about a few millimeters per second every 5 billion years in its orbital energy around the sun. So it really isn't costing anything. So this is a typical type of trajectory that we use for really traveling all over the solar system. We can even use this type of trajectory billiards to go into the inner solar system as well as the outer solar system. We've gotten really, really good at it. So what's so special about this? Well, if you take a look at the formation of the solar system and the accretion process, we wind up seeing small bodies starting to grow into larger bodies through this process of collisional accretion. And sometimes you wind up getting big enough planetesimals where they can start to come together to form even bigger planetesimals. So you go from the initial accretionary impact of small bodies, growing planetesimals a few tens, hundreds of kilometers in size. Additional collisions will wind up creating planetary embryos, maybe thousands of kilometers wide. And eventually you get a planet they can accrete in a few tens of hundreds of millions of years. So actually the planet forming process is really pretty quick. But when we take a look at where this asteroid came from, occasionally these asteroids don't necessarily accrete very friendly like. So you might have two asteroids coming together that are nearly the same size. One smashes into the other and knocks enough material off that asteroid to not only send debris from the crust and upper mantle, but also from its core. And these are asteroids that have gotten big enough and hot enough inside where you're getting what's called differentiation, where the heavy metals sink toward the center and the lighter silicates rise toward the surface. So hopefully with this type of asteroid, we may be actually looking at a fragment of the core of a planetesimal. And this is what it would look like in hand sample. This is an iron meteorite. And these are not that common on the Earth. The stonies are much more common. And we can see this is all iron and nickel. And if you were to reach down to our core of our planet and grab a piece of the inner core, this is what you would bring up. So by taking a look at a bigger fragment like this, we can see how well we can correlate the data we got from these iron meteorites and see what this asteroid is going to help tell us about the formation process in the early solar system's history. It'd be really interesting to see as well what these impact craters are going to look like. Are they going to look like the impact craters we see on like Ceres or Vesta, or are they going to be really exotic looking, like maybe this painting is trying to illustrate? So that'd be kind of an exciting thing to take a look at. So the science goals are pretty important for this one, because up to this point, we have visited a lot of rocky worlds, worlds that are composed of varying concentrations of silicate material, carbon-rich material, such as Vesta right here. We've been visiting a lot of icy worlds, such as Enceladus, one of the moons of Saturn. But we have yet to visit a metal world like Psyche. So this is going to be very, very important because this is going to help us understand basically the building blocks of planets and the planetary accretion process. And we can actually relate the formation of Earth to our understanding of this metallic world. So this is going to be a very, very exciting mission to take a look at. And I know a lot of planetary scientists are kind of anxious to get this thing going. And the nice thing about this, when they're done with it, there's going to be enough data from this type of mission that we'll be able to keep scientists busy for probably a couple of decades analyzing comparing it to Vesta, comparing it to Enceladus, comparing it to Earth, to see what it's all about. So we're going to see how this progression of rocky worlds in the inner solar system, icy worlds in the outer solar system, and these metallic worlds are the product of these massive collisions. So in the operational scheme for Psyche, here's how it's going to work. Within about 100 days of our arrival, the spacecraft's going to start doing a lot of optical navigation, making sure that the asteroids in our proper field of view, and the other navigational stars are in our field of view, so we can navigate to that asteroid properly. And we're going to take a look and make sure that there's no debris around the asteroid. We kind of discovered that not all asteroids are debris-free, as we have found out with Bennu. And sometimes these asteroids may even have small planetary companions, like little tiny asteroids, and that's not too uncommon. So we want to make sure that there's not a big hazard assessment for the spacecraft as they get closer and closer. And they're also going to help to focus in and refine the spin rate of the asteroid itself. So by the time they get there, their initial orbit is going to be at an altitude of about 700 kilometers above the asteroid. Here they're going to do some general mapping of the surface, kind of confirm what the shape of the asteroid is compared to what our computer models are, and what the radar images suggest it might look like. So it's going to be a spherical, it's going to be irregular, what's it really going to look like? And we'll take a look and see what the density of the asteroid really is by taking a look at it and see how it affects the radio signals going back from the spacecraft to the Earth, and seeing how its gravity field kind of affects that by looking at the Doppler shift. Then we're going to take our engines and we're going to lower our orbit down to about 300 kilometers altitude. And now we're going to start taking higher resolution imaging. And this is our orbit B. And this one, we're going to start taking a look at topography. So we got a system on board that's going to help us to measure the altitude variations on the surface of this asteroid to see how rough or how smooth it happens to be. We'll get higher resolution global color maps. We'll refine our gravity science. And we're going to see if there's any remnant magnetic field around it, and how it possibly even interacts with the solar system, the sun's magnetic field. So we'll be able to get a closer view of that. And then after we're done with orbit B, then orbit C, we're going to come on down to about 100 kilometers or so. And now we're going to get even higher resolution imaging of the surface, refining our gravity science and magnetic field mapping. We'll be able to get a closer look at crater age determination. And crater age determination is more of a relative thing, to see how many impact craters there are in a region, and to see how many are overlapping each other. It would be nice to actually land there and get a piece back, but that's not going to happen. We have a gamma ray spectrometer on board that's going to help us to determine what the mineralogical and elemental composition of the surface is. So is it just a iron and nickel rich body, or are there other elements on there, other minerals on there that have been incorporated into this particular object? And then finally, with the final orbit, we'll get down to about a 200 kilometer radius. It'll give us an orbital period of about 3.8 hours. And here, we are going to do some really high resolution mapping, getting really high resolution elemental composition, which in turn will give us an idea of what the elements of the surface are, and in turn map out what the mineralogy of the surface is. We could also do that with neutron particle emission analysis. And again, getting higher resolution imaging, better gravity, and better magnetic field mapping. So we see right now from our observations, Psyche's got an average radius of about 105.5 kilometers and a rotation period of 4.2 hours. So we're going to want to refine that even more as we get to our initial approach period. So now this brings us to Lucy, and Lucy is going to be a far more ambitious mission than Psyche. Psyche is actually a member of the main asteroid belt, whereas Lucy is actually going to the Trojan asteroids, which are along the orbital path of Jupiter. So let's take a look and see what this mission is going to be about.
Beyond the asteroid belt are fossils of planet formation known as the Trojan asteroids. These primitive
Kevin, we can't see any video. We can just hear audio.
Oh, okay. Let's see. You can't see any audio or video?
Correct. We can hear the audio, but we can't see the video. I think it might have opened, the link opened in a different window, which is not being shared on the Zoom.
Okay. Well, that's okay. This is just more of a fun visual. It's only about a minute long, so I'll just continue on. I wasn't sure that was going to happen. Okay. So at any rate, this is what the mission is going to be all about. Basically, one of the asteroids we are going to go visit on the about in the middle of this mission is the asteroid Donald Johanson. And you know your anthropology a little bit. Donald Johanson was one of the anthropologists that discovered the hominid fossil Lucy back in 1974. So that was one of the reasons why this mission is called Lucy. Plus, from what I understand, somebody was listening to the Beatles and they were playing Lucy in the Sky with Diamonds. So that was another reason for calling it Lucy. So kind of a nice history with that. And just like the hominid fossil Lucy was kind of the Rosetta Stone, so to speak, for our understanding of our own hominid evolution, hopefully the Lucy mission is going to give us the same idea about these asteroids and how they evolved in the story of our early solar system. So these are the asteroid targets we're going to take a look at. The Trojans that we see are in the L4 Lagrange point and L5 Lagrange point. And what these are points that are gravitationally neutral, that are balanced out between the gravity of Jupiter and the gravity of the Sun. Earth has one, all the planets have them. So these particular areas are areas where objects can orbit around without being affected by the Sun's gravity or being diverted by Jupiter. And you can see we have two populations, 60 degrees in front of Jupiter and 60 degrees behind Jupiter. And I think they kind of changed the names. I think the ones leading Jupiter are called the Trojans and the other ones are called the Greeks, but that's probably another story. So Donald Johanson is this little guy right down in there. It's part of the main belt asteroid family. They're going to take a look at that. We'll take a look at these asteroids here, Eurybates, Polymele, Lucas, and Oris. And we'll take a look also at Patroclus and Menoetius, which are a binary pair, which is kind of unusual. We want to take a look and see what that's all about. Eurybates, by the way, is the seems to be the parent asteroid of the family of asteroids called the Eurybates. And this seems to be the largest such family of asteroids in the Trojan family. So looking at this particular asteroid is going to be pretty interesting. So this is the Trojan family in relationship to the solar system. And you can see as Jupiter orbits around the sun, it's kind of pushing the asteroids ahead of it and kind of dragging the asteroids behind it. So they're all kind of staying within that area consistently in its orbit. Probably been doing that for, who knows, maybe 4 billion years, maybe longer. One thing to remember that we want to take a look at is if we understand our history of planetary formation, we suspect that Jupiter and Saturn were the two planets to form up earliest in the solar system. But they didn't stay where they were at. They gravitated into the inner solar system, maybe as close as Earth's orbit. And along the way, they disrupted this whole region of rocky material that eventually went on to make the inner planets. And then when they started to drift out, Saturn acted like a big tow truck and helped to drag Jupiter out and finally end up at the orbits they are today. They probably dragged some of these asteroids with them and they got stuck in Jupiter's gravitational field here. That's one possible idea. So maybe visiting these asteroids, seeing what their dynamics are all about, maybe give us another clue as to why they're there to begin with. So this is kind of a wonky, if I can use a term that a colleague of mine likes to use, picture here. To really understand this picture, you have to take a look at this and view Jupiter as stationary and the solar system is moving in relationship to it. So here's the idea with this particular mission, launching in October 2021. We're going to leave Earth and we're going to kind of swing around here and do a gravity flyby, gravity-assisted Earth, and then head on out to the Trojans. And along the way, our first flyby is going to be Donald Johanson. This is a C-type asteroid, which means it's a carbonaceous-rich asteroid, very dark. We'll do that in 2025. Then we'll continue on out, and we're just going to do a flyby of each of these asteroids in turn, starting out with Eurybates. then Polymele, followed by Lucas, and then Orus. Then we're going to leave the L4 Trojans area, come on back down and do a swing by of Earth again, and then head on out to the Trojans, where we're going to take a look at the pair of Patroclus and Menoetius to see what's going on with these two guys. And hopefully the mission will last long enough, or maybe we'll even be able to do a follow-up of another asteroid in this area right here, or maybe a target of opportunity, say a comet, for example, which would be nice. But these are the primary targets for this particular mission. So here's why these asteroids and the Trojans are so important. We have a lot of different classifications for asteroids, and a lot of these are broken down according to their spectra through telescopic observations, and their spectra can give us an idea of their chemical composition, looking at how light interacts with surface elements, and each of those surface elements have a very distinctive fingerprint, so to speak. So with that type of observations, we know that there are a type of asteroid called a C-type, and there are some rare types called B, F, and G types, and these are very dark. This is the Murchison meteorite here. This is a C-type meteorite, carbon-rich meteorite, one of the more primitive bodies in the solar system. And this type of asteroid comprises about 75% of all known asteroids. That's a pretty big chunk. And a lot of them are out beyond the midway point of the asteroid belt. So if you take a look at asteroid Ceres and Vesta, about halfway between those two asteroids is kind of like what they call the frost line, where beyond that frost line, the solar temperature during the early nebular formation is cold enough now where hydrogen and carbon compounds can start condensing out of the solar nebula. So we want to check to see how similar these particular objects are to carbonaceous chondrites. Then there are the S types, and these are 15 to 20% of known asteroids, and these are pretty common. They're called S type because they're made up of rock that has silica in it. They also have iron, magnesium. These types of asteroids are very similar to the crustal composition of our own planet. And there's some metallic nickel iron mixed in with it as well. If you took a look at it closely, you'll see little flakes of iron and nickel throughout here. You'll see little round things called chondrules. These are some of the earliest accretion forms in the Earth's early solar system formation that eventually would lead to a formation of larger planetesimals and eventually to the inner planets that we know today. They are similar to our known as stony iron meteorites. So what we see right here is stony iron is kind of a 50% mix between the iron content and the silica content. In this case, we're taking a look at a type of olivine that's iron rich, and very pretty type of meteorite. And this type of rock we think is coming from the boundary between the core of a planetesimal and the lower mantle of that planetesimal. The M type is a kind of making up most of whatever is the balance here of these, maybe about 5% of the rest. And if we notice, we take a look at their albedo, in other words, how bright they are. The albedo here means that these types of asteroids are reflecting only 3% of the light falling on it, whereas the S types are reflecting 10 to 22% of the light falling on it. And these M types are about 10 to 18%. So we think that the M types are probably nickel iron, maybe similar to the what are called pallasites, or maybe even iron meteorites. And then we have very rare D and P type at the outer edge of the main belt, and this is where we see some of the Trojans that we're going to take a look at. And these also comprise some of Jupiter's small moons, which probably shouldn't be too surprising since Jupiter has a lot of moons that have fallen into its gravitational well as a result of drifting too close to it throughout the solar system's history. These are also very dark, probably on the order of the same albedo as the C types. And these are considered to be ultra primitive, maybe even more primitive than C-type asteroids with primitive organic compounds. And in other words, hydrogen compounds mixed in with hydrogen and carbon within their forming very, very primitive organic compounds. So here's how they compare. We see Patroclus and Menoetius are the two largest in this group at 113 and 104 kilometers in size. Here's Uri bodies. So Patroclus and Menoetius are both the P-type asteroids, and the P-type, of course, are the ones that are very similar to the D-type. These are very, very primitive organic, with very organic type compounds in it, maybe similar to the C-type. And we have your bodies, which is a C-type. So hopefully we'll see how close these types of asteroids compare to a carbon-rich asteroid like your bodies. Here we have another D-type, which is going to be similar to the P-types here in Orcus and Lucas, and another P-type here with Polymele. And then little Donald Johansen is a C-type, and you can see it's only about 2 or 3 miles in diameter. So this is a little tiny guy that we're going to take a look at here. And really, when you take a look at all these objects we're going to fly by, it's kind of a testament to our ability to navigate around the solar system with such extreme precision. We can fly by Donald Johansen probably within about 100 kilometers without any problem at all. And even maybe even get closer if we need to. So our navigational skills have gotten quite refined over the decades. So here we see how they compare in their rotation. So we see Patroclus, Menoetius, Lucas, and Polymele, and even Donald Johansen all have a counterclockwise rotation, like most of the planets in the solar system. But we see your bodies and Orcus are rotating in the opposite direction. This could very well be the result of impacts that have resulted in these clockwise rotations that you don't normally see among larger bodies. It may not be very unusual for these smaller bodies. So here is Patroclus and Menoetius, and these are an interesting pair of bodies because it's possible that these could have been interlopers from the Kuiper Belt that fell into Jupiter's gravitational sphere of influence and got trapped in the L5 position Trojan period. These have been observed for quite a while, and we know that they orbit around a common center of gravity, and their orbital period is about 4.283 days, and their distance apart is about 480 kilometers, and their orbital inclination is about 22 degrees to the ecliptic. And what we see right here is a diagram based on Earth-based occultation observations. So each of these parallel lines here indicates observations from a single observer. Red lines indicate that the observer saw the asteroid pass in front of the target star, and so we wind up using that information to give us an idea of the overall general shape as it passes in front of that target star, and that's known as a stellar occultation. And then the blue dashed line right here is giving us an idea of what the relative long axes of these objects are in relationship to each other. And here's one of our best images of this pair made by the 10-meter Keck telescope in 2005. So you can see Patroclus, it looks like it's a little bit larger than Menoetius. And they're reflective enough to give us a pretty good image with the 10-meter Keck telescope. So what's the question here? Well, why are these two bodies orbiting around one another? Could they have formed elsewhere and then got close to each other within the Trojans and then just kind of fell into each other's gravitational well? Or is there something else going on here that we're trying to figure out? So one thing that we're going to take a look at, we're looking at that right now with what's called the Yarkovsky effect at Bennu, is to see what is causing this. And I'm going to hope that this is going to show up. Let me know if you can see this. Everybody see it okay?
From a distance.
No, unfortunately, again, we can hear it but not see it.
Rats. Okay. Well, maybe I could deal with that a little bit later on. So right now, what we're taking a look at here is what the effect of the heating of the surface of a small body can do to its orbital period and its rotation. So as you take a look at a small body, maybe less than 20, 30 kilometers in diameter, it'll be rotating on a rotational axis, and one side is going to get heated as it faces the sun, and as it rotates away, it's going to cool down. And as it cools down, anytime it's being heated by the sun, it's going to give off infrared radiation, and by the time it rotates around back again, it's going to be cool enough where that radiation is going to start heating up again. And that infrared radiation that's being emitted by that asteroid is enough to get a small asteroid to slow down its orbital period, where it can actually start to lose orbital energy over a few tens of millions of years. Likewise, there's another effect called the YORP effect, named after the scientists who have coined it. And again, we've got Yarkovsky, O'Keefe, Radzievsky, and Paddock. And what they're saying here is that not only can this heating of the sun affect the orbital velocity of an asteroid, it could also affect its rotational velocity as well. So a lot of these asteroids, really, when they come together, nothing more than a big rubble pile. And if you get that rubble pile spinning fast enough, eventually the force of that spin might be enough to start breaking apart that asteroid into smaller bodies. And this is something that could be done by the heating up of the asteroid by the sun, and that infrared radiation being emitted by that surface is acting as like little accelerating jets that over tens of millions, hundreds of millions of years can start to slowly increase the rotation rate of that asteroid, so it gets to the point where the force of that rotation overcomes the mutual gravitational influence of all these little pieces on each other, and the object starts to fall apart, and you see a piece breaking off here, and winds up becoming kind of an orbital denizen of this body that it broke off of. And over a period of time, you wind up getting this pair kind of slowly rotating, getting farther and farther apart from each other until you get this rotating binary pair here. So one thing they want to do with this mission is to take a close look at the dynamics of this pairing and to see just how severe this is, see if it's a process that could have separated these two, or is there something else going on that we haven't really taken a look at yet. And we haven't seen too many of these types of asteroids in the asteroid belt or in the Trojans, as far as we know. And maybe this will help to refine that, that observation. Now, when we talk about the spin-up effect, we see some of this maybe going on at asteroid Bennu. With the OSIRIS-REx mission there, they noticed a debris field coming off of this asteroid, and this was totally unexpected. And the question is, well, what's causing this debris field to come off here? Are there micrometeorites hitting the surface that are causing the impacts? Is there a sudden expansion of water ice beneath the surface causing an expansion and explosive effect like we see on comets? Or is there something else going on? And this could be one example of where the YORP effect could be tossing material out from an asteroid like this. And this could be kind of a model for maybe understanding how a body like the pair that we're going to see in the Trojan 5 Lagrange point is going to be able to answer for us. So speaking of the asteroids, let me go back real quick here. Did I forget something? No, I didn't forget. I thought I had another animation in here. I'll have to check and see. But anyway, a little bit of a back update on the OSIRIS-REx and Hayabusa 2 missions. Right now, Hayabusa 2 has collected its sample return, and they're on their way back to Earth. And they did their sample collection earlier in the year, and they should be back by the end of this year, maybe early 2021. Bennu is taking a little bit longer. Of course, we got there a little bit later on. But as you take a look at the surface of these asteroids, they're much, much rougher than we thought they were going to be. So they had to be very, very careful to pick just the right spot so they don't damage the spacecraft when they come down to take the sample. So if all goes well, we should start taking our sample. I got to get my OSIRIS-REx is in red. So sample collection is being actually made in February 2021. It was going to be made this year, but they've kind of pushed it back to February or so. They'll collect it there, and then they'll head back and be back here by about 2023. So this is the area they're going to sample. You can see it's not too bad, but this is a view that is from an altitude of about 820 feet or 250 meters above Bennu. And we take a look at this boulder right up, this boulder right here, which is about 43 feet in size, okay? So you can see there's a lot of very large debris here. It's not a nice regolith-like smoothness that like the moon has or some of the larger asteroids have. So this is one of the reasons why they were having a hard time picking a good safe spot to land in. So this looks like it's going to be the target. This is called Nightingale Site. And here we see a comparison. This is Osprey, Kingfisher, Nightingale, and Sandpiper. And of these, scientists felt that the Nightingale was the safest one to land on and get the samples that we're looking for. So those are going to be that's the target site for this particular mission. So if we take a look at this, I hope this one is going to work. Let's try and see. Is it working?
Yes, that one is working.
Okay, good. So here we see OSIRIS-REx at Bennu. And what we're seeing here is a mapping of each of these ejection events that they saw. So this was the first one in January of 2019. And you can see the particles get ejected off and will eventually come on back down to hit the surface. This was February 11th, 2019, then August 28th. And then there was one more that occurred in September of 2019. So these are small particles, maybe, you know, there might be some that might be the size of a baseball, maybe smaller. They're not very big, but you can see as they get thrown out, they go on a long looping trajectory because the gravity is so small, and eventually will land back down on the surface of the asteroid. So still the big question is what's causing this, and maybe our observation from the Lucy mission will give us some clues as to what's going on there, including our observations from OSIRIS-REx. Okay, so that kind of gives you a rundown on these two very exciting missions, and I'm looking forward to seeing them myself because of my work with meteorites, to see how well they compare to the meteorite samples that I've looked at and others have looked at. So two very ambitious missions, and we hope they get off in on time and safely and complete their observations. So I will hand it back over to, where am I? Oh, here I am. There we go. I'm going to close this off. There we go. Trying to navigate my way around here.
No problem.
There we go. There we go. I got it. Okay.
There we go.
It was up at the top. I couldn't see it.
All right. Well, thank you very much, Kevin, for that fantastic talk. I believe we have some time for questions and chat. Everyone's muted right now. If you have questions, want to unmute yourself. If you'd rather submit questions through the chat, that is fine as well. But let me just make sure that everyone is able to. Yes, you are able to unmute yourself. If you have a question or want to say something, please feel free to do so. No questions?
Hi, can you hear me? This is Audrey.
Yes, Audrey, we can hear you.
Yeah, great. Yeah, I'm on Android here. But anyway, thank you for the wonderful talk. Even without the visuals, I got a clear picture of what was going on, and I really love it. And I can't wait to go back and listen to it again with visuals when I have my computer available. But asteroids, this is so awesome. First of all, like you said, it is so cool that we can actually navigate so well to these places and actually come back with a sample. It's like a dreamland of what our scientists are capable of. But have they ever considered putting a camera, leaving a camera on an asteroid and letting it go off and take a tour of the universe and just get feedback? And also, Trump was, I hate to say that name, but he was talking about the possibility of actually mining the asteroids. Would that be kind of sacrilegious? Would we want to do that? Or maybe if it's a dangerous asteroid, we'd want to break it up and take it home? You know, what are the thoughts on this? And could it be like a mini spaceship, or somebody to actually sit on an asteroid? And I don't know. What are the possibilities for asteroids?
Yeah, there are a lot of possibilities here. As far as leaving a lander on the surface, putting a lander on the surface is a bit tricky. Of course, when you put a lander on a spacecraft, you're adding mass to the spacecraft. So you have to decide what it is you want to do there. And we have left objects on the surface of other bodies. The Rosetta mission left a small lander on its comet, and the near-Earth asteroid rendezvous actually wound up landing on asteroid Eros. But you know, right now when we start taking a look at the budgets that we have and what we want to do there, you know, putting a lander may not tell us a whole lot because we're going to be stuck in one spot, and that asteroid really isn't going very far. You know, putting a lander on a comet is one thing because it comes in close to the sun. You can see the activity going on, and then it goes down and gets quiet again. An asteroid is pretty much quiet the whole time, especially out there in Jupiter. So it would be nice to put a lander on the surface of an asteroid, maybe with a little rover on it. Maybe that'll be done sometime. But right now, it's not in the budget. And as far as the other ones, well, who knows what will happen down the road? There's always been talk for the past half century of mining asteroids because of the resources that we might find there, which will help to give our own planet a break. And if we ever become a spacefaring society, that might be the way to do it because our resources can only last so long before they get used up. So that could provide a whole litany of issues and possibilities down the road.
Yeah, thank you for that. And but one of my questions was actually putting just a simple little camera on it, just to relay information back if we'd learn anything. But like you said, maybe it's kind of quiet and empty, not much to see. But you never know.
Well, the problem with these small bodies is that they do have a very small gravity field. So putting a sub-satellite in orbit around them is a possibility. But then you have the issue of communicating with it, and the smaller your spacecraft, the tougher that might be. But with the technology developing and with the microsat industry developing the way it is, it could be a possibility down the road. We just actually demonstrated that with our MAVEN mission to Mars that deployed a couple of microsats to assist in data relay to see how it would work, and it worked beautifully. So maybe something like that will be possible down the road.
And being we're so close to an election, does NASA have an official list of candidates they're supporting or not, or are they not allowed to talk about that?
Since they're a government agency, that's something they kind of steer clear of, because that could get tricky.
Yep. Yep.
Yeah.
We do have a question from the chat. Will PSYCHE be attempting retrieval of samples and returning it after its trip to the first Trojan group on its second pass by to Earth, dropping it off on the way to the Greek asteroids?
No, these are all going to be flybys. They're not going to be orbital. So in order to collect, you have to put something in orbit, like it did at Bennu. So that will not be done here. And
then one other from the chat, there's a side question, which is just why are the gas planets so large and the rocky ones so small in comparison to each other?
It basically depends on where they are forming the solar system. If we take a look at the solar nebula as it's first forming around the sun, your denser materials, your higher temperature materials are tending to be more rocky in the inner portion of the solar system, inside the orbit of the asteroid belt. And outside the asteroid belt, you're getting colder conditions where you wind up getting a lot of now hydrogen and carbon compounds. And hydrogen is a very dominant element in the universe. So if you have the ability to condense hydrogen out of the solar nebula, then you got a lot of material to build a big giant gas planet. Where you don't have that in the inner solar system because the conditions are just too hot for hydrogen compounds to start condensing out of the solar nebula.
All right, well, those are all the questions from the chat. Unless anyone else has any other questions or comments they'd like to make. And if you do want a refresher on this, I just want to shout out that it has been recorded. We will be posting it to the CERN Center YouTube page. The previous 2 CAS meetings are posted on there already. So feel free to check that out. You can find the link to it on our Facebook and get there and watch the old CAS talks. And then probably in the next week or so, we'll have this one up there for you to rewatch later.
Thank you so much, Wayne, for hosting, and thanks a bunch to Kevin. Very interesting. We'll be following this for the next couple of years, and again, you know, thank you so much.
It was a pleasure. I really enjoyed it.
Good.
Technical problems aside.
Yeah. Well, actually, it went kind of smooth compared to.
Yeah.
Yes. Okay. Well, Joe Malik liked it. Says thanks for a great presentation.
Good. I enjoyed it.
Okay.
All right. So with that, thank you everyone for joining. And I believe, it looks like we lost Jim Kuga. But the next Say Yes meeting, I believe, is scheduled for tentatively October 23rd. Keep an eye again on the CERN Facebook and webpage. We'll keep you updated on who the speaker is and final dates for that. So thanks once again for attending, and hope to see you again next month.